In psychology, we're interested in humans. That would be what you could call our target population. Now, typically, what we do in our research studies is we select a relatively small group of individuals to participate. We would call that the sample. And samples do tend to be similar to the population from which they're taken, but that's not necessarily going to be the case, because whenever you take a small group of something from a larger group, there's always a chance that that small group could be full of weirdos. And having a sample full of weirdos is going to distort, your picture of what the population possibly looks like. So just to be clear, a population, that term, that refers to the entire set of individuals of interest to a researcher. Although the entire population usually does not participate in a research study, the goal of our study is to try to understand that population. Like, we're going to generalize what we have learned to all the individuals that we didn't get to study. And the word sample, that refers to that set of individuals that have been selected from the population. And our sample is usually intended to represent the population. They're like a little focus group, so to speak. It's just like a small group of people that are there to, be representatives, to put it simply. Now, populations and samples have this kind of relationship where if you get a good sample, it can tell you quite a lot about the population that they come from. So the selection of good, representative participants is critical when it comes to research planning. The outcome of your study may depend entirely on the method you use to select your participants. And always remember, you want to the main reason why you want to have good participants is so that you can generalize from that group to the larger population. So, in other words, you want to have what's called a representative sample, a sample with the same characteristics as the population. And the more representative a sample is, the better you can do that, the better you can generalize to the population. But the real trick is trying to figure out exactly how representative your sample is. The researcher must determine how well this, sample actually represents that target population. Unfortunately, in a lot of cases, samples are not very representative. They are what you would call a biased sample, a sample with different characteristics from the population. This is that group of weirdos I was describing earlier. So, to put it another way, the individuals in your sample maybe just generally they're older than most people in the population, or they're faster, or they're smarter, or they're, a particular demographic group that is, not representing everybody else. The thing about biased samples is if you just take people randomly from the population, you could very easily get one. A biased sample could occur simply by chance. I don't know exactly how they produce Skittles candy, but just imagine this. Imagine in a Skittles factory, they take their empty bags and they just randomly assign Skittles. Like, it could be any color. They just randomly put them in there, right? I doubt that's how they do it, but just work with me here. So they randomly put different colors of Skittles in there. If it is purely random, then that means you could open up a bag of Skittles and it could be entirely red. Just nothing but red Skittles. And if that's the first bag of Skittles you've ever had, you would conclude that all Skittles must be red. Obviously, that's not true. And I think you see where I'm going with this. You want to make sure that your sample is a good one, not one that's just randomly determined. Random determination can result in some pretty biased samples. because improbable things happen all the time. We like to think that if we leave everything up to chance, it'll all work out in the end, because in a lot of times it does. Things do, just by random nature, tend to balance out over time. But you're not doing that kind of over time balancing. You're taking like a snapshot. You're taking one group of people at one point in time, and you're trying to use that group of people to understand the population. So you could get a very biased sample. You could get a bag full of red Skittles. It's unlikely, but it could happen. Remember, just because something is improbable, that doesn't mean it's impossible. And humans typically have some difficulty when it comes to things like probability. So all I'm trying to say here is just don't leave it up to chance. Now, one of the best things you can do when it comes to getting a good representative sample is to use a sufficiently large sample size. The researcher's goal is to try to maximize that representativeness, and they can do that by taking advantage of the law of large numbers. So this is something I was talking about just a moment ago, when I was saying that if you do something enough times, it'll balance out. If just left up to chance, it typically balances out. That's basically what this law of large numbers is about. So what this says is that the larger the sample you get, the more all those weirdos in there will balance each other out, and your sample will become more representative. So simply by having more people, you're going to be getting a more accurate measurement of your population. And typically what we find with most studies is that if you have a sample size of 25 to 30 individuals in each one of your different groups, then that's going to give you a fairly representative sample. Here's an illustration of what I mean. So on the y-axis, we have the difference between the population and the sample means. So as you go higher up on the y-axis, there's a bigger difference. In other words, it's less representative. And along the x-axis, you have your sample size. And you can see that if your sample size is very small, if you have only one person in your sample, it's very likely that that one person is not going to be normal. They're going to be to one extreme. They're going to be a weirdo. Everybody is a weirdo. If you look at people individually, everybody's pretty weird, right? But then when you get two weirdos, they start to balance each other out. 3 balances out even more. It's kind of like, they're compensating for each other's extreme behaviors and extreme attributes. And all that balancing just gets better and better over time until you get around 25 to 30 participants. That's where it's balanced pretty much as good as it's ever going to be. You don't really get much benefit from having a sample size larger than about 25 to 30. Now, that's one of the most important things when it comes to research, is just making sure you have a good representative sample, and typically you can do that by getting a sample of about 30 people. Another really critical issue when it comes to doing research is knowing exactly how you're going to measure the things that you're interested in. This is especially relevant when it comes to psychological research, because a lot of the stuff we measure is kind of hard to see. So what we use are called operational definitions. This is a procedure, it's a set of instructions for indirectly measuring and defining a variable that cannot be observed or measured directly. Now, an operational definition specifies a measurement procedure for measuring some kind of external observable behavior. In other words, what we're doing when we use an operational definition is we're saying, I'm going to measure this thing that I can't really see by looking at stuff that's related to it that I can see. It's hard to see an intelligence. You can't really look at a person and see intelligence, but you can look for behaviors that we believe are related to intelligence. Like if people do very well in school, if people get really high marks on intelligence tests, that's something we can observe. And we believe that those things are related to intelligence. So our operational definition then would be, that your score on an IQ test can be used to measure that thing we call intelligence. Now, exactly how you go about measuring variables is something that takes a lot of consideration. Operational definitions, they do typically indicate exactly how you want to measure that variable, but you have to make some decisions, such as, do you want to measure it in a quantitative fashion? A quantitative variable is one that is typically measured by assigning a number value to the individual. Like with the IQ test, we're assigning that individual a number that indicates some quality that they have. Other quantitative variables would be things like your height, your age, your GPA, those kinds of things that we can put a nice number on. But then there are categorical variables, and these are things that we can't really put numbers on. That wouldn't make any sense. Categorical variables are things that we assign like a label to. So, for example, your gender, that would be a categorical variable. Your ethnicity, your religion, your political affiliation, your major in college. These are things that we can group you up. We can put you into different categories, but it doesn't really make any sense to put a number on something like that. Now, when it comes to what we do with these variables, when we're doing research, what we're trying to do with these variables is try to see if they have some kind of interesting relationship. And the term we use is statistical relationship. That word statistical, that's a very important part of it, because when we say that two variables have a statistical relationship, what we're saying here is that when one score changes, the other score will also change in some way. So the average score of one variable differs across the levels of another. The numbers seem to go together in some way. So that's typically what we're looking for. There are some types of research where we're only measuring a single variable, but it's much more common, you'll see in the research, that we're looking for these kinds of statistical relationships. And there's two kinds. There's two kinds that we tend to talk about. The first of which is called between groups differences. You could also call that significant differences. That's where we look to see if these two groups have some difference along some variable. Like maybe one group is faster than the other, maybe one group gets higher grades than the other. We're just looking to see if these two groups are different in some way. And then the other kind of statistical relationship that we tend to look for is something called a correlation, or you could just call it a significant relationship. And a correlation, that just refers to when two variables seem to change at the same time. So maybe they change, like when one variable goes up, the other one goes up, or when one variable goes down, the other one goes down. But just to go into a little bit more detail, those between groups differences, that's the difference between the mean scores of two groups on some variable of interest. And a wide variety of research questions take this form. I just wanted to include a short list, but unfortunately I couldn't fit it all on the screen. There's just so many different things that you could potentially do when it comes to between groups difference. This is by far one of the most popular research designs that you'll find out there. And then a second basic form of statistical relationship is that correlation between two quantitative variables that I described a moment ago. This is where the average score of one variable differs systematically across the levels of another. Again, there's a wide variety of research questions in psychology that take this form, such as, is being a happier person associated with being more talkative? Do children's memories for touch information improve as they get older? And so on. There's so much research that's been done using the correlation design. I'm sure you've already seen and heard about a lot of these kinds of results. And you're talking about a correlational design if you see something like this. So this is called a scatterplot. This is the most often way correlational data is presented. It's a chart wherein each point on that chart represents a single individual's score on two quantitative variables. So in this little example chart I have down here, you can see that the participants who scored low on their IQ test also scored low on their GPA. And the individuals who scored high on GPA scored high on IQ. So this would be indicative of a moderate strength correlation. You know, the dots, they form an upward trend, but it's not a perfectly straight line. There's some variability there. So there's a lot of different ways we could go about measuring a correlation, but one of the most common, the most standard way to measure a correlation is called the Pearson's R correlation coefficient. So this is a number. It's a statistical value that measures and describes the direction and the strength of the relationship between two variables. And this number ranges from +1 to -1. Now, the number tells you two things. The absolute value of the number describes its strength. So if it's close to +1, it's very strong. If it's close to -1, it's very strong. And if it's close to 0, then it's very weak. Now, that's the first thing it tells you, is how strong it is. The second thing it tells you is how these variables are related, which, you know, how does changes in one variable affect the other. So if it's a positive number, that indicates that they're changing in the same direction. When one variable goes up, the other one will also go up. That's a positive correlation. A negative number would indicate that they're going in opposite directions. So when one variable goes up in value, the other variable will go down. Now, that's basically all there is to it. Pearson's R correlation coefficients are incredibly simple conceptually, but it is a little bit confusing for new students. So I just wanted to show you this illustration. Remember, as the coefficient goes up to 1, either positive or negative, it gets stronger. And as it gets closer to 0, it becomes weaker. So this is what we call the relationship's strength, or the correlation's consistency. That other thing that it tells us, the direction, the polarity, whether it's positive or negative, that tells us how these two variables are related. So if it's a positive relationship, if it's a positive correlation, then as one variable increases in value, the other one will also increase. And then of course a negative relationship would be the opposite. When one variable goes up in value, the other one goes down. So if you see a scatter plot where the dots are going up and to the right, that would indicate a positive relationship. But if in that scatter plot the dots are going down and to the right, that would be a negative relationship. So I just wanted to show you a few examples. I think it's helpful to just get a sense of what these different kinds of correlations would look like if you were to put them in a scatter plot. So here's an example of a positive relationship. Now, the more time, this research is stuff I made up, but the idea here is the more time you spend running on a treadmill, the more calories you'll burn. We can probably assume that there's a correlation there. So calories lost should have a positive correlation with time spent running. And if we were to go out and collect data, maybe it would look something like this. That looks like a pretty nice, fairly consistent, positive correlation. If we were to measure the Pearson's R of that, I would expect it to be somewhere in like the 0.9 range. So yeah, I would say that this is a pretty strong relationship. Now here's an example of a negative relationship. The more time you spend procrastinating, the lower your GPA will likely be. So as time spent procrastinating goes up, we should expect GPA to go down. So let's pretend we went out there and collected some data, and here's what we found. So yeah, once again, this looks pretty consistent. I would also expect that to be in about the 0.9 range, but now negative, because it's a negative kind of relationship. That data is going down and to the right. And then here's an example of what your data would look like if there was no relationship between the variables. In this study, we were looking to see if the number of tacos you eat had an effect on your IQ score, if those two variables are related in any way. So as tacos eaten goes up, we'll see how IQ score is affected. The answer is not. It's not affected. There doesn't seem to be any kind of relationship here. If we were to measure the Pearson's R, we would of course get a number, but that number is incredibly close to 0, so I think we can conclude that there's not a relationship there. And then finally, there's one last type of relationship I wanted to mention, and that's called a spurious relationship. You could also call it a coincidence. This is when you find a relationship between two variables, like these two variables appear to change together, maybe even in the same direction, but they're not actually related. So in this example, we're going to see if there's a correlation between ice cream sales and physical assault. So we go out there, we collect the data, and we find that yes, when physical assault goes up, ice cream sales goes up. It's actually a fairly strong relationship here. Maybe it would have a Pearson's R of 0.91. This kind of research has actually been done, and these are the kinds of results that they actually have found. So when you look at stuff like this, it really makes you wonder what's going on. You know, is the consumption, the purchasing and consumption of ice cream, is this driving people crazy and making them want to hurt each other? How can we explain this correlation? I'm sure you already had many ideas of your own regarding how these two variables could possibly be related. And if you're not sure exactly what the real explanation for this is, we'll come back to it. But yeah, these two variables are in fact related, but not in the most obvious way. This would be an example of a coincidence. And there's a lot of examples of coincidences out there. Like we find these kinds of spurious relationships all over the place, such as the more Nicolas Cage, the more films Nicolas Cage appears in, the more people will drown by falling in a pool. Clearly, we need to stop Nicolas Cage from appearing in films. People are dying as a result. Obviously not, but you get the joke. Here's another coincidence. As the total U.S. crude oil imports increases, as we import more crude oil, so does the per capita consumption of chicken. And I know you realize this isn't true, but for a moment there, you probably imagined maybe we're cooking the chicken in crude oil. Like, even, that's obviously ridiculous, but for just a moment, you tried to find a connection there. I'm sure you did. And maybe that was the connection you thought of. Here's another example of a coincidence. The more money that the US spends on science, space, and technology, the more people commit suicide by hanging, strangulation, or in suffocation. Obviously, we need to stop teaching science. People clearly can't handle science and they're killing themselves over it. That's not the case. But for a moment there, you probably made that connection. And that's the big problem. That's the big problem here, is that when people hear about two variables being related, they naturally want to make sense of it. They naturally want to, connect the dots, so to say, and try to explain this relationship. But you need to really try hard to refrain from that impulse. Just because two things are correlated, that doesn't mean that one causes the other one to change. Correlation does not imply causation. With all those examples I just mentioned, Nicolas Cage appearing in movies, obviously it's not causing people to die. There's some other explanation here. So whenever you hear about two variables being correlated, just try to keep in mind, maybe this is a Nicolas Cage situation. Maybe those two variables, they're changing together, but they're not actually affecting each other. There's a bunch of reasons why we shouldn't infer causation from correlation. The first of which is called the directionality problem. Just because a research study has established a relationship between two variables, that doesn't mean that we know which variable is the cause and which is the effect. Like, let's say we find a correlation between X and Y. It could be that X causes Y to change, or maybe Y causes X to change. We just don't know. We can't know unless we use a different study design. No correlational study will ever be able to determine directionality. Another big problem with doing correlational research is that there might be a third variable. The third variable problem refers to the fact that there may be a variable that you didn't even measure that is the causal factor of both X and Y. So this third unidentified variable might be producing this apparent relationship. Or to put it another way, X doesn't affect Y and Y doesn't affect X, but they change at the same time due to the influence of Z. So those two reasons alone are clear reasons why you should not try to make sense of a correlational study. If a researcher comes out there and says, you know, we've conducted all the survey research and we found that these two things go together, your response should be, okay, what does that mean? That doesn't really mean anything. All it means is that you notice these two things change at the same time. It quite literally means nothing, right? Like, it can actually be very frustrating to read correlational research because you spend a lot of time collecting the data, and at the end of the day, all you have to say is, I don't know what's going on here, but it certainly looks kind of interesting. And people want to know what's going on here. People want to understand cause and effect. That's a natural human inclination. So the way you get around this is by not doing a correlation. The way that you avoid these problems is by simply doing an experiment. If you want to study cause and effect, if you want to know which variable is causing effects in another, you have to do an experiment. It's that simple. So you manipulate one variable, and then you observe the effects of your manipulation on another. If your manipulation seems to produce some change, then congratulations, you've found a causal relationship.